This video is looking at the equations in P1. And in P1 for GCSE there are four main equations that you need to understand. The first one is the equation for specific heat capacity, which is usually written as energy is mass times specific heat capacity times the change in temperature. So change in temperature usually is written in units of degrees C, but it could be Kelvin because it's a change in. And we can have another little equation that goes with this, which is that change in temperature is equal to final temperature minus initial or starting temperature. So if you want to know what the change is, we always do final take away initial. So sometimes the question will be calculate the final temperature, and so you have to use the E equals mc delta T equation to work out the change in temperature, and then you have to add it to the initial temperature to work out the final. So we have energy as well, which is always measured in joules. We have mass, which is in kilograms, and then that gives us specific heat capacity, which has units of joules per kilogram per degree C. Now, when you're thinking about specific heat capacity, it's important for you to associate that with the amount of energy that a material can store. The actual definition of specific heat capacity is the amount of energy required to raise 1 kilogram of a material by 1 degree C. So that comes from rearranging the equation to give you C is equal to E delta T. However, if a material like water, for example, has a high specific heat capacity, what that means is that it can store a lot of energy. It requires a lot of energy for it to be heated up a degree, but also it means it has a lot of energy stored, so if it's cooling down, it will take longer for that material to cool down. The second equation, which is very similar, is also about energy, but this time it's specific latent heat. So E and M are the same thing, but L this time is specific latent heat, and there are two types of latent heat. Okay, the first is latent heat of fusion, and the second is latent heat of vaporization. So fusion is the energy required to either melt or freeze a solid into a liquid or a liquid into a solid, and vaporization is the process of turning a liquid into a gas or vice versa, so boiling or condensing. So fusion is solid into liquid, but it can go either way. Now if it's going from a solid to a liquid, which is melting, then bonds are being broken, and if it's going from a liquid to a solid, bonds are being made, and it's the same for a liquid to a gas, and the bonds that are being broken when this occurs are intermolecular bonds. So what happens when a material changes state is the temperature doesn't change. So unlike this equation where there is a change in temperature, when a material changes state, the temperature stays constant, and the reason is that energy is being used to break intermolecular bonds or make intermolecular bonds as it's changing state to go from a solid to a liquid or a liquid to a gas, etc. So specific latent heat is what we associate with changes in state. And the latent heat of fusion and vaporization are different because it takes a lot more energy, for example, to turn water into steam than it does to turn ice into water. The next two equations are not related to heat. The first can be, and it is efficiency, which we usually just write as efficiency, but there is a letter that's used for efficiency, which is a nu, which looks like that, but usually we quite often just write efficiency. Efficiency is useful energy divided by total energy times 100. So it gives us a measure of how much of how useful a particular device is at carrying out its function. So for example, a light bulb, how much light energy does it give out compared to how much electrical energy goes in. Another way of thinking about this is quite useful is that sometimes useful is sometimes just described as the output. Sometimes they just sort of directly say that the output of a device is a number, and that it's that output is useful, and the total can sometimes be considered to be the input, because quite often there's only one source of energy input. So for example, electrical energy, and that's what you put there. So that's the equation for efficiency. And then the last one is the equation for wave speed. So again, totally different topic. So wave speed is measured in meters per second, and it is the frequency, which is the number of waves per second, and is measured in hertz, multiplied by the wavelength, which, remember, the wavelength is the distance between two peaks, or the distance between for one complete cycle to have taken place. So wave speed is frequency multiplied by wavelength. We can often obviously rearrange that and have frequency is wave speed divided by wavelength, and wavelength is wave speed divided by frequency. With this particular equation, bear in mind that quite often they will use standard form, because for electromagnetic waves, the frequency and the wavelength are often quite large. So as an example, you might have a wavelength, for example, given to you for visible light. So for example, 3 times 10 to the minus 7, that would be just outside visible light. That would be violet, or starting to be ultraviolet light, meters. So that's the wavelength. Obviously, you can use a calculator and show that that is 0.0000003 meters. So if you can't do standard form and don't understand it, it's important that you have a look at that for the purposes of that particular equation, where it's quite often used. So just one extra thing I just want to do in this particular video is just show you an example of the difference between specific heat capacity and specific latent heat with this question. So Sam takes a 0.2 kilogram block of ice from a freezer. The question is, how much energy is needed to turn it into steam? So we've got to go from ice to steam. Now, we start off with the ice at a temperature of minus 18 degrees, and we're given a whole series of information about specific heat capacities and specific latent heats. So the way to think about this is if I just sketch a heating curve, so I've got time, I've got temperature. At the moment, our ice is down here at minus 18 degrees. And first of all, we've got to heat it up until it reaches 0 degrees, where it will then turn from ice into water. Then we've got to heat it up to 100 degrees, and then we've got to boil it, and then we've got to turn it into steam. So there's a couple of stages we've got to think about with this. First of all, we've got to provide it energy to get it to 0 degrees. So to do that, I've got to use a specific heat capacity equation. And so initially, my energy to get us from minus 18 to 0, I'm going to call this energy A, just for the first stage, call that A, is going to be 0.2 times the specific heat capacity of ice, which is 2110, times the change in temperature, which is 18. So if I do that on my calculator, 0.2 times 2110 times 18 will give us an energy of 7,596 joules. The next stage is to go from here to there. So we're going to call it stage B. And this is obviously the stage associated with melting the ice into water. which is what it's going to be at that stage. So we use the specific latent heat equation for this. So the energy is going to be the latent heat of fusion, or for melting in this case, of water, which is 334,000 joules per kilogram multiplied by 0.2. So put that into my calculator and we get 66,800 joules. You can see that as considerably more energy to change state than just to heat up the material. I've then got to repeat the process again to heat up water from 0 degrees to 100 degrees. So it's going to be 0.2 times, this time the specific heat capacity of water, times 100, which is 84,000 joules. And now the last stage to turn it into steam is I've got to undergo the latent heat of vaporization. So I've got to do 2,260,000 joules. Obviously you can see it takes a lot of energy to boil water, and I've got 0.2 kilograms of water to boil, so that gives me 452,000 joules. The total energy needed is going to be all four of these energies added together. So that's 84,000 plus 66,800 plus 700, so 7,596. So we get 61,396 as my answer. Just remember that latent heat is always associated with changes of state, and specific heat capacity is to do with heating up a material. You can see from this that it takes a lot more energy to break the intermolecular bonds in water to form steam. That is by far the biggest energy requirement in this process. It doesn't require nearly as much energy to melt ice into water, and it is much easier to simply heat the material up.